Hey, am I audible? Okay, let me check. Check, check. Hello. What's up, boys? Am I audible? Let me check. Hello, hello. Okay, okay, it's fine now. So voice is fine. Okay, let's go then. Let's don't waste any time. Let's go. Okay, so let's see what we have got for today. So yeah, we have got the second variant of yesterday's problem, XOR after range multiplication queries. And, so yesterday we have we did it using that brute force approach, but I think today we'll head to that TLE because okay, so yesterday's and today's I think constraints are same. Li, vi, this. Okay, that's same here. Hmm. So let's first do it using brute force, and then we will think for uh, the optimized solution. And, so yeah, what we have asked, we are given an integer array nums length of n and a 2D integer array queries of size q where queries I is li ki vi set index is equal to li, okay, while index is less than equals to ri. Okay, we have to do this and update nums of index is equal to nums of index into vi, then modulo 10 raised to power 9 plus 7. And then we have to move the index by ki places, है ना? And we have to return the bitwise OR of all elements in the nums after processing all the queries. So yesterday what we did was mm, yeah, we just used that brute force approach. Let's go for the brute force first. So first of all, what do we need? Do we need anything, right? So let's loop all the conditions like queries. So for and I is equal to 0, I less than queries queries dot size and 5 plus plus. So end left is equal to queries of I 0th index. So what left we have then? Okay. Okay, right we have right is equal to queries of 1 will be there. Then we have k, int k, that will be third element, and then int value 3. So what we have to do is while left is less than or equals to right, and left should be less than nums dot size, है ना? Or do I need to check it with the num size, because right will always be less than or equals to, sorry, less than, and I think we need to check this condition. So what we have to do is nums, we have to change it. So long val equals to star nums of left star value, then nums of left equals to value modulo mod. Okay, we have to declare a mod, and const mod equals to 19 plus 7. Here we go. Okay, 19 plus 7, it's there. And left plus equals to k. Do we need to do anything else? No. So, int result equals to 0 for int I equals to 0, I less than nums dot size, height I plus plus, result is or equals to nums of I, then return result. So it was like the brute force is this. I hope what I did. Did I? What I did was update nums of So this brute force has given us this time limit. So um, okay, we need to think for a more optimized solution. So as yesterday I was talking about that offline range queries, but here the problem is that the index is variable, like the range is not fixed. The pattern which I solved questions was that there was a fixed range and there the operations was of one kind. Like here we have to multiply by different values of k, and as well as we have different indexes. Mm. So we need to figure out something which works here. And the hint, okay, the topic is principal array divide and conquer. So hint one is that for b, for k less than equals to b, where b is the square root of n, group queries by k l mod k. For each group, maintain a difference array of length seen in by k to record multiplier updates, then sweep each bucket to apply them to num. It seems complicated. Yeah. And hint 2 is for k greater than b, for each query set index is equal to l. Well, do index this. Okay. So where from where this logic arrived? Let's see if we have like approach square root decomposition for difference array. How do we get this intuition? Yep, yes, totally agree. Make the tutorial or solution to put some text of how you come up with this idea. While of course many based on experience, we need to know how to get that experience. Yep. Which is unfortunate. There are other ways to test skills without relying on pure competitive code programming. I have had interviews at major quant firms and they don't make you use a square root decomposition. Okay, what that it's saying the experience would unfortunately come from competitive programming, which tends to be a step higher than what most people would look for. So how do we approach this question now? So here we are given the intuition. The most straightforward approach is to simulate each query directly by multiplying elements one by one, and the time complexity for the single query is order of n. For queen queries, it becomes order of n cube, which is around 10 raised to the power 10 and will lead to a timeout. Yeah, the main issue is that when k is small, a single query accesses many elements, making it expensive. Yeah, the main issue here is that it accesses many elements, which makes it expensive. That is the thing. We observe that step size k affects the complexity differently and handle each query separately. So here we need to, like, first of all, we have to identify the which part of our logic, which is like hitting the time complexity to a upper level. So we have like figured it out that that size of k, if it is very large, it will access very few elements. Mm. Now we have to like deduce a relationship between k and root n and handle each category separately. So for some yeah, for some value of k, if k is greater than or equals to root n, so what we have to deduce the relationship between k and n. We have to get this. We have to get the relationship between this k and n. So okay, let's suppose we have l equals to 0 and r is equal to what the heck, like r is 20. Yeah, r is 20 and n equals to 21. Fine. So if k is equal to 1 or k is equal to 1, how many how many element I will access? How many times? Like if right, left, so 20 minus 0 upon 1, that is 20. When k is equal to 2, 20 minus 0 upon 2 equals to 10 and k equals to 3, around 6. So how we are hmm, and what is root 21? 4 4 is 16, 5 5, like it would be around 4 something. So 4, when k equals to 4, we have 20 minus 0 upon 4, that will be 5. And when we have k is equal to 5, we have 20 minus 0 upon 5, that is 4. When we were 1, we got 20. When we were 2, we got 10. When we were 3, we got 6. When we were 4, we got 5, then 5, then 4. So here we have got something like when k is greater than root n, each query touches at most n by k, which is like less than or equals to root n. So a brute force is acceptable. Okay, this is the thing. But when k is less than root n, a single query accesses many elements. Yes. So one thing I'm getting is that we are grouping such queries which are taking which are accessing a lot of elements, and we are trying to eliminate that part only. Hmm. So for smaller step sizes, k less than root n, we group queries by their k value so that queries with same k can be processed further. And okay, but wait a second, that is the thing which hit me. Okay, and the key observation is that indices affected by same k form a fixed pattern. For example, k is equal to 3, affected indices will be L plus 3, L plus 6. Yep, that's it. Once k is fixed, each query multiplies elements at positions LLL. This is equivalent to performing range multiplication on a subsequence defined by a step size k. Okay. To handle this efficiently, we use a difference array like difference initialized with all values set to 1 for a query LRV. We determine the last affected index and denote the next position as R. For example, in the query 273, the last affected index is what? The last affected index is say left, right, V. V is what? Here V minus 1 is modulo using after processing all queries for a fixed k, we traverse the difference array and compute prefix products. Okay, let's give the cumulative multiplier for each position. This is something technical. Wait. So we are uh, grouping all those queries which have same value of k. This is something complicated. Differently, we did the queries into two queries based on the relationship between k and root n and handle each query separately. When k is greater than root n, each query touches at most n by k. Yeah, this is here we up to this point it's clear, and up to this point also it's clear. And this is represented by the CMK form of fixed pattern. For example, k is equal to 3, L plus k, L plus 3, L plus 6. Once k is fixed, each query multiplies elements at position L plus k, L plus 2k by V. So this is equivalent to performing range multiplication or subsequence defined via step size k. Yep, this is also clear. Up to this point, it's clear. Now what we are doing to handle this efficiently, we use difference array. Difference array initialized with all values set to 1. Okay, we have just uh, like we have a difference array, and for a query LR we determine the last affected index and denote the next position as R. Capital R. Okay, for example, in the query 273, which key like starting will be 2, value is 3, so the last affected index is 5. How it is difference of L is equal to difference of L into V and difference of R into difference of modular inverse of V minus. Yes. Hmm. Which can be composed in format little theorem as okay. After processing all the queries for a fixed k, we traverse the difference array and compute prefix product. Difference I is equal to difference I into difference of I is equal to difference of I minus what is this thing? this part, this part is so difference I is equal to difference I into difference I minus k. This is the part. Uh, One thing I have figured out, am I slow? Okay, so I have got this thing. We have L, R, and K. Like left will be like let it be 2, let it be 7, and K will be 3. So the first will be 2, the next affected index will be 5, and then next will be 8. So up to this is valid. So here we'll be doing it this one. So this will be in range, and this is the like index which will nullify this effect. Like here we will be multiplying with V, but here we will be multiplying with V inverse, modular inverse. I got it. Something I am getting here, if I'm multiplying here with 3, okay, and I am multiplying it with 3 inverse, right? Here I will be multiplying with 3, 6, 15, and inverse will be cancelled, so it will be just 8. One thing I got here, difference I is equal to difference I into difference I minus k. Okay, this is the multiplier which we got, and we have to use this thing. The maximum possible value of R is n plus k. For convenience, we use a difference array of size n plus t. Yes. So the overall approach, what I got. So one thing is that group all similar k whose L is less than or equals to root n, then for L less than equals to root n, compute the difference array. Compute the difference, and then the rest brute force, then apply difference array in original array, right? Now this is the overall idea. So I need to code this part, and the coding is the real part, right? What they have. What? Just a second. Just a second. Okay, so let's go for the coding part. Okay, I just got a message from a placements group. Okay, just a second. Let me reply. Okay, do it. So we have got this approach, like how we will be doing this, how we'll be solving this problem. Now we have to do is that just code the thing. Uh, So this was the brute force approach. Now let's go for this. And it was like same for the there was a हाँ दोनों लोग हैं. So now what I have to learn is this coding part, like how to like code these hard questions and time constraint. And I think I have like how much time I have given, like 34 minutes I have given for this problem. And and not just understand. I have just taken the help of the editorial as well. For convenience, what is the t size of t? What's the t here? Square root decomposition plus difference array. Okay, do I need to have some on this? I need to like go through the code as well because it's quite we give what they are doing. So they have given int is equal to nums dot size t is square root of n. Okay, vector in groups. I need to take it. I what they are asking. It's a I need to keep it for not rewind. I need to create a list. Uh, okay. I need to add it into the complicated part. What's this thing? So we'll be moving to so guys I need to okay there is an urgent work so I have to go for today.